In this last video of section 11.1, we're going to look at how to do a four-step example of a chi-squared test for goodness of fit. Before we do that, let's remind ourselves of the conditions we need to check before we do our calculation. So this is part of our plan, the plan step in our four-step process. After stating the inference procedure, in this case, which would be a chi-squared test for goodness of fit, if conditions are met, these are the conditions we need to check. So randomization or randomized experiment, random sample. We need to check that we're not sampling more than 10% of our population, assuming we're not doing an experiment. And then the last one is the expected counts, not the observed counts, but the expected counts, assuming the null hypothesis is true, all must be greater than 5. Remember, too, that we are using counts and not proportions. So we don't look at the individual p-hat values, we look at the individual count values, observed and expected. Also, remember that when we are checking the large count, a common mistake is people look at the observed counts that they all are bigger than 5. It's not, it's the expected counts. So the last thing we want to talk about before we start the example is sort of the null hypothesis and alternative hypotheses. So remember that we're going to the null hypothesis is always that like what we think is going on is correct, or what the standard thing is going on is correct. Sometimes we'll get that information from a website or from a company or kind of common sense. The alternative hypothesis is going to say pretty much the same thing as the null, except we're going to have a not in there. Okay. The chi-squared test statistic calculation is shown there. Remember that we get the p-value from the chi-squared table using a degrees of freedom of k minus 1, where k is the number of categories, not n minus 1, the sample size. All right, so here is the example. In his book Outlier, Malcolm Gladwell suggests that hockey players' birth month has a big influence on his chance to make it into the highest level of the game. Specifically, since January 1st is the cutoff date for Youth League in Canada, where a lot of the NHL players come from, players born in January will be competing against players up to 12 years younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more play time, and as a result, more coaching and better success at being a hockey player. So if we, to see if the birth data is related to success, and success here is going to be judged on whether you make it into the NHL, we take a random sample of 80 hockey players from the National Hockey League, and we record their birthdays. We record how many are in each quarter. So we're breaking the year into quarters, and we're going to look at how many of those 80 are in each quarter. Now I'm hiding this data, the sample data right now, because I want to emphasize the fact that we're going to pretend we don't know this data before, while we're writing our null and alternative hypotheses. So we want to know if this data is going to show us evidence. But before we think about that, we want to think about what the null hypothesis is. So the null hypothesis is, before we read Malcolm Gladwell's book, we would probably have thought that the birthdays are all equally distributed. There's no reason to think otherwise. So the null hypothesis will indeed be that the birthdays of all the players are evenly distributed, so we would expect the same number roughly in each of the 4 quarters. The alternative hypothesis will be that they are not evenly distributed, okay? All right, so now we can look at the data, and we'll use this data to do our calculations. To do that, we need to check, first of all, make sure that you've written down, I didn't do it on the last slide, but make sure that you have your alpha level listed on your state. And now we want to look at the plan. So the chi-squared test for goodness of fit is going to be the inference procedure that we're dealing with. And so we want to check the 3 conditions. So the first one, yes, we randomly selected the players from the NHL. Number 2 is the 10% condition. So we would have to assume that there are at least 800 players in the NHL, and in this particular year when this study was done, there were indeed 879. So that's good. And then the last count is the third count, is the large count condition. We have to make sure that the expected values are all over 5. And indeed, we would expect if they were evenly, if the null hypothesis is true and they're evenly distributed, then yes, indeed, we would expect 20 in each of the quarters, and indeed, that is more than 5. Okay, so to do, go ahead and calculate that using the same procedure that we did for the M&M's calculation. We see here there are 4 categories, so there's 4 separate calculations. We add those up and we get a chi-squared statistic of 11.2. Now, how do we calculate the p-value from that? We could look at this, a typical graph. It looks something like this. And we can look at the table, and we look at the degrees 3 line of our chi-squared table. This gives us p-values that are between 0.01 and 0.02. We can use our calculators to take our chi-squared statistic and get our p-value from it. We can go to distributions. That's the second vars button, and go down. Normally we use a lot of normal CDF and those kinds of T-CDF. Now we want to do a chi-squared CDF. It will ask you for the lower value, the upper value, and the degrees of freedom, and that gives us a value of about 0.011, which is in agreement with what we saw up here. Even though we knew it was between these 2 values, we knew it was closer to 0.01 because 11.2 is pretty close to this end value of 11.34. So they sort of all agree. You can use on your calculator, you can draw the distribution as well, like we could for a t-distribution. If you have a newer operating system, or an 84 with a newer operating system, then you can don't have to do any of this by hand. You can use the calculator to do the whole test for you. First thing you're going to want to do is put the observed and expected values into list 1 and then list 2, making sure that they correspond across from each other. Then we're going to go to your stat button, go over to tests, and go down to chi-squared GOF, which is the goodness of fit test. You're going to tell it what table, what list you have your observed data in, what list your expected data is in, and your degrees of freedom of 3, and you ask it to calculate, and it will give us this outcome here. So that's the chi-squared statistic. The p is the p-value, and the degrees of freedom. The next thing listed there is actually a matrix, and it's called the contribution. We'll talk about that more on the next slide. All right, so what should you do on the do part of your 4-step process is say that you're using your TI calculator, tell me that you're using which test, the goodness of fit test. You are giving me the degrees of freedom. You're giving me the chi-squared value, the statistic, and then the p-value along with a curve with shading. Not much shading shows up here because our p-value was so small. Okay, so the conclusion is very similar to what we saw before in other significance tests. I'm going to give you a second to try to write that or pause the video. All right, there's 3 parts to this as usual. The p-values compared to the alpha, it's less than in this case, so we, as a result, will reject the null hypothesis. This means that we have convincing evidence of the alternative, and we say that in words. And in this case, it's pretty easy because the alternative was written in words up in the state part of the process. Okay, so this is not all we want to do in this case, but since we rejected the null hypothesis, we want to know, we want to do a little bit of a follow-up analysis. We want to know, like, okay, so what were the where were the differences? So in other words, we rejected it because the differences in the observed and expected values in each of the quarters, the differences in general were big enough to create a chi-squared statistic large enough to cause us to reject the null hypothesis. So we want to know where those biggest differences are. And so we'll use that contributions to do this. So if we did it by hand, we would look at the 4 values that we add up to get our chi-squared. If we used our calculators, it gives us a little matrix that we can use the right cursor button to go over and look at all the values. And so not only do we want to know, like obviously there's a big difference in the first and third quarters because you can see those numbers are the biggest. In other words, 7.2 is a big part of what made up the total value of 11. 3.2 is also fairly big, so we might talk about both of those. The other quarters were rather small. Those 2 were rather small, so we don't have to worry about talking about those. We don't want to just talk about where the biggest differences are, first quarter and fourth quarter. We want to talk about the directions of those differences. And so a good follow-up analysis for this particular example would be that there are more than expected NHL players with birthdays in the first quarter and less than expected in the last quarter. Looking just at the contributions themselves don't really tell us what direction they're in, so you would have to go back and look and compare your expected and your observed values to determine the direction of those. Okay, and this is the homework. Make sure that you're looking out for any 4-step problems.